morning, everybody. How are you doing this morning, Virginia? You said last night that you could use some more practice on doing Lewis structures. And I'm sure most of the class can use some more practice doing Lewis structures because depending upon the 113 course you took, you may have covered that like the last week of class, even though it's one of the most important things that you need to carry with you. When you don't do an atoms first approach in Chem 113, it's kind of the thing that you cover last and it's covered in a hurry. So what I need to know from you guys as you go forward is, I told you that I was going to be setting up to do a series of podcasts and recording other videos to augment this for review and stuff. Would that be a good topic for podcasts? Would it be a good topic for me to do a series of short 10-minute, 15-minute lectures on how to draw a good Lewis structure, how to know if a Lewis structure is good, how to determine molecular shape, and so on and so forth? So pop that in the chat. Let me know if that would be a good thing. That would go in terms of teams. That's why there's that section. Oh, I need to fix that. Give me just a minute. So in teams, that type of thing would go in, I'd probably, well, damn, I can go ahead. It'd probably either still go in module 0 or I'd add a new module called review podcast or something. But I'll put it where it's easy to find. And I'll add I do have the chapters there. So the review chapters are there. But I would probably shift these two review chapters to the new module, or add them to that module as well, and do the podcast. So if you really would like some podcasts on Lewis structures and molecular shape and how to determine that as a review, just again let me know in the chat, and I will get on doing that on Saturday, Sunday, and Monday, which are holidays, so I can spend some time doing that. So don't forget to check in, please. And just a reminder to everybody else, admittedly, the Teams looks different on a phone or an iPad. And that's another thing. If you want a podcast about how to navigate Teams using a phone or an iPad, pop that into the chat. Because we are definitely going to be running Teams now. So you need to let me know if you need a review, if you want review and stuff like that. But don't forget to check in. checking to see how many. Okay, we've got at least 16. That's about half the class. Okay, so don't forget to check in. Now, here's the next thing I need to talk to you guys about. And I'm going to put this as a poll in Teams, and I'm also going to put it as a link into this. So I told some of you guys that my mother is ill, and that's part of the reason why the college was willing to start testing hybrid courses. And she got a poor scan, so I'm going to need to be spending time at home, taking her to doctor's appointments and so on and so forth. Well, at their home in Tennessee. But, you know, we've already got the course set up to be predominantly online. There are some in-person meeting weeks that are not during the weeks of exams. That may have to adjust and change. Don't know yet. I will keep you informed if the calendar changes. But it is what it is. But what I would like permission to do, now that I see what my time is going to be like in terms of trying to keep track and manage Gen Chem 1, Gen Chem 2, with this on top of it, with 2 research students that need 12 hours of my time per student, because they're both in upper level research classes. I would like permission. So I'm going to flip us back to Teams real quick. So right now, the way the course is set up, in terms of grading, I'm supposed to be writing bright space quizzes, and they're supposed to be worth 150 points. And the truth is I don't think I'm going to have time for that. So what I'd like to do is fold this 150 points into the homework and just increase the homework percentage up to 350 points. But since this syllabus, we've been working under this syllabus for 3 weeks, this is something you guys get to vote on. Because this is a change that I cannot make without class permission. Now, luckily, it can be the class permission of the students actually attending class, but it is something that you guys have to give permission for. So basically, the homework right now is worth whatever I said it worth. I didn't actually put what each. So like the homework this week was worth 15 points, but you could get a 22 out of 15. That would have given us 150 points, 10 homeworks, 15 points each. Now the homework would be worth 350 points with some bonus, which we've already got. You can see how I do that, which would be a balance and actually give you more bang for your buck because you're already doing homework. So here's what you get to determine, and I'm going to post this into the link. That's the other thing you get to determine. So the link that I just posted is do I have permission to transfer points allocated to multiple choice quizzes to homework? And then, do you still want me, when I get time, and I will work to get time, to upload the multiple choice problems as practice quizzes where you can play with them, but no points, just you can go into Brightspace and use it as you want, or practice final, but you get multiple attempts on the practice final where you see the multiple choice questions. And, you know, if I'm not giving multiple, well, so you can choose that. This is on this response. And that's the reason why I'm saying practice quizzes and taking the time. But it's a lot easier to upload practice quizzes, because then what I do is just I upload the entire bloody test bank and ask the test bank to just randomly pull, 15 questions, and you take them. So then every time you go in, you've got a 15 question practice quiz that's different questions from a given chapter. So it's actually a lot less time for me to give you guys access for practice quizzes than it is to actually write online quizzes where I go through and pick very particular questions and so forth. So it takes less time on me to just make the test bank available to you, basically, than it does to actually write a formal quiz. I know that seems odd, but in the world of uploading stuff, it is actually easier to upload a test bank as a whole than it is to pick individual questions. Oh, if I do practice quizzes like that, I'd make it where you can just, I'm going to make it where I can't even see your grade. I'm going to just make it where you can just take it ad nauseum. As many times as you want to take it, you can take it. Because, see, they're there for you. They're not really there for a grade. And because of that, I'm not even going to set them up for I see the grade. Okay, so please respond to the survey that's posted. And I put a link in the chat. And there's also a link in the Microsoft Teams under classwork. So it's under Module 1 because we're swapping into Module 1. So we are now out of Module 0 and into Module 1 for finding all your links. We are still discussing that. The issue is there a computer lab that we can have for enough time to give the final? So we are still negotiating with the college for that. But yes, our desire is for the final exam to be online in Brightspace. It just saves paper. It saves a huge amount of time. But you would still have to come into a computer lab and take it out on campus. You're not going to be allowed to take it at home. I just needed to say that because you're absolutely not going to be allowed to take the final at home, but it may still be computerized. So again, we are in Module 1. Just want to put that out there. So now when you're on Teams and you're looking for your links to office hours for there we go. If you're looking for links for office hours, lectures, the whiteboard, and various polls and stuff that we're doing right now, it is part of Module 1. And then when we get to Module 2, things will move to Module 2 and so forth. But we are in Module 1 at this point, and we will be here for a while. So the things that might change, I don't know yet. So depending on how you vote, these quizzes that are due on Sundays at 10 p.m., they go out the window. Um, and so we'll still be meeting this week, Monday, March 9th through the through March 11th. God, that's wrong. That's not March 22nd, obviously. I'll fix that when I'm making changes. We'll still be meeting this week, week 7, because that's exam 1. What may change is this in-person meeting may go to online. These 2 in-person meetings, week 8, week 9, may go to online. It's just going to depend on treatment schedules with my mom. But the weeks that we have exams will obviously be in person. Everything else, I don't know right now. I will know more next week when my mom meets with her oncologist. But that's why this course was a hybrid. And since many of you guys left, like, as soon as I gave homework time on Monday, I'm guessing mostly online is not going to be upsetting to most of you. For the 6:30 to 8:30 to be at night to be online, for the most part. So, any other questions? The finals, being an online final, is predominantly about paperwork. So when we give department finals, Rinston, just to let you know, when we give department finals, those exams, because it's a 50-question multiple choice exam, those exams are usually 6 to 8 pages long, maybe 10, depending on the questions. And you know, it doesn't seem like that big a deal. There's 35 of you guys. So, but 35 times 10, that's 300 pages of paper. And then if you then take in the other sections, we're going through about 1,200 pages of paper just for the final exam that literally right after the final exam we shred. So it's really wasteful. And the amount of time it takes to do multiple versions and Xerox multiple versions and randomize multiple versions for the exam in a room, it's a time-consuming deal. So if we can do it as a computer, it just streamlines everything and reduces waste. So that's why we're leaning that way. But I will keep you informed as I know. Let me see real quickly how you guys voted, since 22 of you have voted. Okay, we are going to be moving all of the multiple choice to homework. Absolutely. That's 100% change. And practice quizzes and also practice final. I'll still probably do the practice final with multiple attempts with a test bank, because that'll also let us debug the actual real final. And I'll make that available to the other classes as well. So, okie dokie. That works. And I appreciate that. Sometimes you have a brilliant idea in your head, and when you start in class, you realize, oh God, this is not going to work. What am I going to do? So I appreciate you allowing that pivot. The homework will work exactly like it did this week. So I'm going to post suggested problems this afternoon. And those problems will be out of the guided inquiry book, because similar to before. So I will reiterate, if you haven't gotten your book yet, or you've ordered it but it hasn't come in, you need to chat me in Teams privately with your receipt, so that I will upload. I will send directly to you through that same private chat the CHEM activities from the guided inquiry workbook, and I will do that until such time as your workbook comes in. I don't have a receipt that you bought it, you won't be getting it. And you saw what the homework was like. Because we are now in the textbook, and the textbook has some decent problems. I'll also be putting suggested problems and things from your textbook. I will tell you, though, a good starting point for your textbook. So, since some of you looked confused when I mentioned this, so for Module 0, I had put a readings ranked by importance, and I will do the same thing for Module 1. And this readings, let it load, basically takes the OpenStax textbook, takes every section in the chapter from the OpenStax textbook, every subsection. Now, OpenStax does not number the subsections, they only number the sections, but it's a list in Word, so it automatically put it A, B, C. I was like, that's fine, I'm not fighting with that. So I ranked the sections. 1, very important. 4, don't bother with it. And I also, on the ones, I put them in red so that you see them, because those are the things you really need to study for an exam and for the final. And I will continue to do that. But that also gives you, when you're looking at your readings for this upcoming module, that gives you, when I rank these, in these readings, you will find there are links to certain simulations that you can play with. You're welcome to go and play with those. It can help. If you're a visual learner, those type simulations can help a lot. As we begin to do quantitative problems, we know that students struggle with quantitative problems. We know from last semester's final that the average on the final exam for the qualitative questions was 10% higher than the average on the quantitative questions. So we know you struggle to do math. So as we hit concepts that are mathematical, if you're struggling not with the concept in the science, but with the mathematics of that concept, that's again another thing that you can put in question and answer and request a podcast on it. I have the books and can write in script fairly quickly a math tutorial lesson on any of this stuff. I am a mathematician, but you've got to let me know what you need. So as we work through, but the thing I do want to show you are these examples. So it has this example, it walks you through the solution to the example, and then it has a check your learning question, and it provides an answer. That's for any section where I highlight it and say this is a number 1 important section, you should automatically work those problems. Now I will probably also assign them, but these check your learnings and sections that I tell you are absolutely going to be on the exam, you should work. You shouldn't ask, you shouldn't question, it shouldn't have to be part of the suggested homework. These should be automatic things that you work. So I did want to point that out. Now, for the OpenStax book, in the course information, you'll see you have the full textbook, and I put the full textbook there because the solutions to a lot of the end of chapter, the answers to a lot of the end of chapter problems are in the back of the textbook. So I did want to let you know that. Not the solutions, but the answers. Okay, so what we're going to be covering in terms of the OpenStax textbook is Chapter 9, Chapter 12, Chapter 13. And you might be thinking, well, we skipped a lot of chapters. We skipped 2 chapters, 10 and 11. The OpenStax textbook is oriented a little bit differently than the textbook that I prefer, which is Gilbert. So in Gilbert's textbook and some of the other Adams First textbooks, this would be Chapter 10, Chapter 11, but then they shift equilibrium all the way to like 14. And the issue is, where do you put solutions? Liquids and solids, solutions and colloids. Some books put that between thermochemistry and thermodynamics. Other books put that between thermodynamics and equilibrium. And other books put it somewhere else, because it's kind of this weird thing of, where do I put this? So I just decided, in terms of examination and how the stuff flows, it's better to teach thermochemistry, thermodynamics, and equilibrium, the fundamentals of it, as one unit. And the reason for that is equilibrium arises out of thermodynamics. So that's why I'm teaching this as a 3-step unit, because we will derive equilibrium from the equations of thermodynamics. So it kind of goes together as a story. And then once we have that, we can use what we've learned there to better talk about what makes a liquid, why is it harder to deal with, what makes a gas, what makes a solid, and phase transitions between that, because those are equilibrium states. So it'll actually make it flow better. So that's why we're doing this way. Given that, I will also remind you, because of this approach, if you hit stuff in the lab that I haven't yet covered, pop your questions in the question and answers channel in Teams, and that can be the questions you're asking, or questions about your lab and how to analyze the data. And you could even ask, could you do a pre-lab lecture on this lab, because I'm not really understanding it because we haven't covered it in class. Now, if you ask that, I don't have the lab manual. So if you're asking me to do a pre-lab on a lab, please also share in your question and answer the lab manual, so that I can do that, because I don't have it. So that's something you would have to provide me with. So that's the general announcements. I'm going to open the floor to questions, because we're at the 30-minute mark. So Pomodoro, 5-minute break. And then we'll start thermodynamics. Oh, break. There we go. So, no questions? You've got 3 minutes for those of you that haven't checked in. And also, don't forget so the check-in form is pinned to the top of the chat. And the form about structure is pinned. Alex ebook, it's is it CHEM? Um, Napstablook 4918. Yes, please. Um, so that's a good question. I'm going to flip it over to whiteboard real quick to answer that question. So what he's asking, or she, crap, live chat up, is if you have a formula like CH3CH2CH2, and just for the sake of being complex, I'm going to do that. CH2CH2CH2. So say you have something like that. That's a pain to write. And this is part of the reason why organic chemists write this as 1, 2, that's 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2. That's part of the reason why organic chemists write this like this. But what you are asking is it okay to write CH3, CH2, CH2, CH3, and 1, 2, 3, 4, 5. Make an organic chemist laugh. That needs to be CH. CH2, 1, 2, 3, 4. CH3. Absolutely. That's a perfectly valid way. Now, sometimes to make it really, really clear what's going on, you'll more formally, if you're going to use this type of notation, you'll generally more formally see this CH3, CH2, CH3. You'll see a bond here, a CH2, 4, a bond, and a CH3. And that's just the reason why that's a more formal, a slightly better way is when you put it like this, some people are going to be like, wait, how in the world did you attach 4 CH2s to that carbon? Now, most organic chemists know what this means. It's just putting a clear bond between that chain shows that much more clearly. I would count either of these, but this is the better way. Okay? Fatima for Chang, please chat me, remind me what your ebook is, because we have used Silberberg in the past and we've used Chang and Oxtoby. Let me know which book it is, and I will let you know what chapters you should be reading. Okay? Because that book I don't think is Adam's First, but the chapters are still there and the material's still the same. They move a little bit of stuff around, but for the most part you'll be fine. You just need to know what chapters to look at. Okay? And if I know what book you've got, I can tell you what chapter. And that's true for everybody else. That's what the chat's for. That's also what Q&A's for. A question like that where you supply the textbook and say, what chapter should I be reading out of this textbook, is a perfectly great question for the Q&A, and then you get your question and answer points. Because somebody was saying, well, what if I don't have any questions? That's a question. Good question. Okay? somebody else asked me for one, I'm going to do one more thing. So somebody else asked me, would it be possible to have PowerPoint slides to help summarize these chapters as a way of being able to, write notes. Now, I don't have time to make PowerPoint slides, and it's not inherently natural to the way I teach to teach with PowerPoint, although I am using PowerPoint in the Q&A, because that way I can share a PowerPoint with the people that are part of the Q&A, and they can write questions in the PowerPoint and I can answer them. But with that being said, most textbooks supply PowerPoint slides for instructors to use. And I'm going to see if Gilbert does that. And if they do, I'm probably going to upload those slides into Teams and you guys can use them as needed. But you're going to have to sort them, and you're going to have to decide based on my lectures and what I list in the readings as important, which slides are important and which slides aren't. But I'll at least provide some slides if Gilbert does. But I was going to let you guys know that as well. If you use it, great. And then the one other final thing I'm going to remind you guys of in Teams is in the general channel in shared. This is where all of your files live. So under class materials, you'll see old exams. These are all of the old exams from previous years. And I may even upload some even older exams to there. The textbook lives here as well. These planner pages are there as just files, but you're welcome to use any of these pages that you think would be useful. They're just provided to you if you want to use them. That's that first readings. So all of the, and then of course the suggested homeworks. So literally everything that I link in classwork that's a PDF or anything else also tends to end up in, I need to make a bonus and move these to bonus, but it also tends to end up in the general shared channel, because that's how Teams organizes. So it's there for you. I just wanted to make sure you knew that. Okay. Now, let's get on to a topic that I teach at many levels. So thermodynamics is an area of research, is the area that most of my research lives in the thermodynamics realm. And so the research I've been doing over the last many years has been predominantly in the realm of thermodynamics. I teach thermodynamics at this level, but I also teach it at the technically junior level. So it's technically a 200 level course, but it's really probably more ought to be a 300 level course. I also teach it. Teams is definitely, I find it more manageable on the desktop, but you certainly can do it on the phone. But I like the desktop setup better. But anyway, but download the app on your desktop too. In thermodynamics, that's kind of my area of research, and I also teach it at the master's PhD level. And the truth of all of those levels is the moment you think you understand thermodynamics, you don't. So the point behind this is a really complex, nuanced, very nuanced subject. You're not going to get it in this first introduction. A lot of the stuff we're only going to be able to basically roughly derive because you guys haven't had calculus, which is required to derive it from real first principles. But this does arise out of quantum mechanics. So you can link thermodynamics to quantum mechanics. Ironically, thermodynamics was discovered first because in order to actually develop, in order to do the experiments that showed us about the atom and the nucleus and the electrons and bonding and everything that built into quantum mechanics, we actually had to develop an engine. And engines work via thermodynamics, and so do vacuum pumps. So we actually developed all of the equations for thermodynamics empirically, which meant observation, observe, notice a pattern, figure out the math that will give you that pattern. Here's the equation for that. And then, 50 years later, when quantum mechanics was developed, and you start applying, you take your quantum mechanics and you apply it to a large number of particles, out pop these same equations. It was actually it's what showed that quantum mechanics and the math and what they were discovering about the atom had some basis in reality and wasn't just a mathematical fever dream. And is, in fact, the fact that you can get lost in mathematical fever dreams when doing theory is the reason why you can't win a Nobel Prize based on theory. So somebody has to show that your theory is applicable to experiment and really explain something fundamental that's never been observed before experimentally for your theory to be a Nobel worthy. But you may have to wait a long time for somebody to actually be able to develop the experiment. And that's in fact why Einstein did not win the Nobel Prize for Relativity, which is what he's most famously associated for today. Because it hadn't been shown yet when they gave him the Nobel Prize. So anyway, the thermodynamics is a complex subject, and we're only going to kind of skitter across the surface of that subject in this class. That being said, if you want to do well in this material, you need to be uber careful when reading questions. I'm going to be uber careful when framing questions, and you need to be uber careful when reading them, because nowhere else in this course is language more important than thermodynamics. So that's what we're going to cover today, is what makes language so important. Now, the first chapter on thermodynamics has historically in freshman chemistry been divided into two parts. A part called thermochemistry, which has historically been put in the middle of Gen Chem 1 for reasons I have no clue for why. But this is basically, yes, I know it's Gen Chem 2. Thermochemistry is actually normally taught in Gen Chem 1. But again, for reasons I don't have a clue why. But this is basically all about the first law of thermodynamics. And then your next chapter, which you usually get to in the kind of the middle, and again, I don't know why they put it in the middle historically, of 114, is a chapter on thermodynamics, and that's what they call it. And this is all about the second law of thermodynamics. Now, there is a third law, but the third law is not really a law, it's a definition, although technically it's considered a law because it could, quote, be disproven experimentally, except it can't. So it's really more of a theorem than a law, but we'll talk about that. So these two, if you really want a true story about these are all the same subject, and that's why from a perspective of a physical chemist who teaches this routinely, it never made sense to me why it was divided the way it was in freshman chemistry. And the Adams First books, where they put these two chapters kind of together, make a lot more sense and make it actually a lot easier to teach. Now, some of you, if you had 113 with somebody else, you have covered the thermochemistry chapter, so this will be review. If you had 113 with me, we covered the very brief intro to thermochemistry at the end of the semester, and now we're covering it for real. But we're going to cover both of these chapters at the level you need to know it. So, anyway, let's talk about these laws. So the first law. Now, so in mathematics as a whole, as a subject, as a field, is built on things called axioms. And axioms are things that are not provable. They are things that you just have to state and take as true. So, the fundamentals of math. So, you guys know that 2 plus 2 is 4, right? And 1 plus 1 is 2, and 1 plus 2 is 3, and so on and so forth. Arithmetic, in other words. Well, arithmetic is built on a series of axioms called Peano's axioms. You can look them up in Wikipedia. And the first Peano's axiom depends on if you're reading the historical Peano's axioms or the more modern version. But the first Peano's axiom is 1 is a number. Today, some books will say 0 is a number, but 1 is a number. Now, you're thinking, well, yes. Can you not state the obvious? But you got to start somewhere. And the first place you start is you got to define the first number. And then the next axiom is the successor to 1 is a number. Okay, see, we're still just defining what a number is. And then the third axiom is the successor to the successor of 1 is a number. And from that, you can build addition. So you can prove addition with those 3 axioms. And then from addition, you can build subtraction. And from subtraction, you can build, in addition, you can build multiplication. So that's how this fundamental set of axioms actually builds all of arithmetic. Now, that doesn't mean that proving any of this stuff is easy. It's a pain in the rear end, and it can take a page to prove that 1 plus 1 is 2. But it can be proven from a set of axioms. But those axioms cannot be proven because, in essence, those axioms are definitions. Now, in science, technically, we cannot prove anything. Everything you do in science is subject to something that might show that it not be true. And that was really kind of the division between math and science. In math, you could prove everything. In science, you couldn't prove anything. And then what happened in the mid-1800s, I think, is when Gödel showed this. Gödel showed that there's stuff in math you can't prove. And it was a real issue. I mean, you want to talk about cause a whole bunch, an entire generation of mathematicians to panic. Gödel, a mathematical philosopher, showed there are problems in mathematics that cannot be proven. And that is actually fundamentally important for mathematics, that it not have everything provable. So, in science, nothing can be proven. But the truth is the first law, the second law, and definitely the third law of thermodynamics, I would say they're more in line with axioms. And I would say that because fundamentally what they're really doing is they're defining vocabulary. And because of that, it's more in line with something that you use to build other stuff on versus so it's more in line with a mathematical axiom than, and I think for the most part these are truly the most fundamental laws, but I think for the most part most things that we call laws are in line with that. They're just fundamental statements from which everything else you build from. Now, if at some point there's a contradiction in what you're building, you do have to go back and look at your fundamental misconception, your fundamental law. And that's why I think they still call these laws. But thermodynamics has been around a long time. And for the most part, it's a well-established field. So I would say these are more axioms than laws. But that's splitting hairs. So the first law is there's one constant, and I'm not gonna define it the way your book defines it. I'm gonna define it in the most general sense possible, and then I'll explain what your book says. There is one constant. Not really. There is one constant in the universe we will call it energy. Now, you might be saying, but wait, we got all these other fundamental constants. We got the perfect gas constant, we got the speed of light constant, we got Planck's law, we've got all these other fundamental constants. But almost all of those fundamental constants are related to energy. And we've got Einstein's wonderful theory of energy equals mass times the speed of light squared, E equals mc squared. So in the end, everything can be tied back to an energy, even mass. So the one true fundamental constant in the universe, we're just going to call it energy. Now, that's a great. The universe is huge. So while that true, and that's why I'm saying the first law, when written this way, it's more of an axiom. Because I can't measure the energy of the universe. Well, sort of we can't. But in a lab, I don't care about the energy of the universe. Let's put it that way. In a lab, I care about the energy of the energy that's being released by the reaction that I am dealing with in the beaker that I am looking at in this laboratory, or the heat that's being released from this hot metal that I'm about to have to handle, or the heat that my stove is supplying to water, and when is this water going to boil because I need to cook pasta. In other words, I don't care about the universe, I care about what I'm looking at. So the first law, when written this way, which is the most correct way to write it, is more of an axiom, but it's also pretty much not useful. So we're going to come back to this and now begin to use it. But the moment we do that, we have to begin to really pay attention to our language. Written this way, don't have to pay attention to the language because the universe is everything. The second law states the ways of distributing energy throughout the universe is always increasing. This distribution of energy we will call entropy. We have this constant energy, but we're going to keep increasing the buckets that we can put this energy in, so that we spread the energy out over time. Now, when you define the second law this way, you don't run into the problems you run into if you say entropy is an increase in disorder, which is probably how you were taught about entropy in high school. Entropy is an increase in disorder. Well, the problem with that definition is then you look around the world and you go, but if we started with a Big Bang, if the universe started with a Big Bang, so we had this nothing and then there's something, and that Big Bang distributed mass and energy and everything all over in an expanding explosion. That's why we call it the Big Bang. Why do we have solar systems? Why do we have stars? Why do we have this? I mean, if you look at the beautiful pictures from the James Webb Telescope, why? Give me just a minute. Crap. I sometimes forget that I have to, in this whiteboard, it's a little bit inflexible. So, this was the first picture from the first what's called deep field image from the James Webb Telescope. I pulled this from Wikipedia. So, if we start with a Big Bang and we talk about entropy as a increase in disorder, why do we have that? Because the Big Bang, we already had disorder. We had disorder everywhere. So why did stuff merge into stars and galaxies and all of this wonderful things? Why does this exist if entropy is an increase in disorder? So that's why I don't teach entropy as an increase in disorder, because it can't explain this. It can't explain this. Oops. Okay. Oh, good, it holds and then stays. So if you think about entropy instead more correctly as a way of distributing energy, well, the interesting thing about that is, and we will talk about this when we talk about solutions, is when particles interact with each other, there are more ways to distribute energy than if you have a particle that's not interacting with anything. So there's technically more entropy when particles are interacting with each other than there is when they're not interacting with each other. So by particles coming together to form molecules, so you can see in the Big Bang we just had energy, and from energy came mass, and from mass all of a sudden now we have atoms, and from at least hydrogen, and from hydrogen, because hydrogen's a proton and an electron, simplest particle. And then all of that started collecting, and then under gravity we get fusion, and then under fusion we get all the other elements. Why? Well, one of the reasons is, as all of that happens, we're distributing all that energy in the universe in a different way. And by distributing it in a different way, we're kind of decreasing the energy locally. We're kind of smearing it out, in other words. Instead of having it in this big pile, we're smearing it out. So if you want a visualization of energy of the universe and entropy, go look out in a parking lot and look at that pile of snow that hasn't melted in a week. That's the energy without entropy. And then think about what would happen to that pile of snow if we would actually go spread it back out again. It would melt faster because it would be able to interact with the sun and other things, and it would go away sooner. So, I mean, it's not the greatest thing because energy doesn't go away. You can convert it to mass and mass to energy, and you can just partition energy into work and heat, and you can do stuff. But the energy of the universe is constant, so you can move energy around, but you can't get rid of it. But the point is if I can spread it out more, it's just a more stable situation. At least that's our understanding of it as humans. Now, the third law, most people, some books actually don't even call it the third law. They just say, but historically it has been called the third law, really is an axiom. If entropy is always increasing and it's a distribution of energy, we sort of need to set a zero. At least if we're going to be able to measure entropy in a lab. So the third law sets that zero. So the third law says, and this one we have been able to show, at least theoretically, from quantum mechanics. And so that's why this law is very specific. So the third law says the entropy of a perfect atomic crystal at absolute zero is zero. So that is basically just setting the entropy, giving us a place to measure entropy relative to in terms of a lab. And it's absolutely vital that that entropy be tied to, it's got to be atomic, cannot be molecular, and it's got to be at absolute zero. And that means it's going to be a solid, and that's why it's a crystal. Now, you are going to see when you look at your thermodynamic properties at 25 degrees C, I was just flipping through the table to look and see. You will see that there are some aqueous solutions that have negative entropy. And we will discuss how that happens, because that's entropy relative to something. But this is a zero, and it gives us a place to start. The reason why it has to be atomic is molecules, even at absolute zero, have vibrational energy. And so they have other ways of distributing the energy. Atoms don't have vibrations and rotations. They only have translational energy. And in a solid, that translational energy goes to zero. So that's why it has to be an atomic crystal. It has to be a solid, and it has to be a solid that's composed of atoms. Usually speaking, it's going to be defined something like helium or hydrogen or argon. So, let me answer this. And we're at a good stopping point, so So we're at a good break point. So we're going to break and let you ask questions. So at this stage, in terms of questions about how to navigate teams, where's the homework and things like that, I'm not going to cover that in lecture. By the way, I'm just curious. Oh, I haven't actually looked to see what the calendar looks like if on the iPhone Teams app. Okay, so those of you that have your phone, because I just had another question on this and we are in break. So, in your phone, at the bottom, if you're on an iPhone, so at the bottom, you'll see CUNY Hub, Activity, Chat, Assignments, Team. You might see Teams, you might not, but you'll see a triple dot. So anytime you don't see Teams, if you hit the triple dot, you will definitely see Teams. And then it should load up a list of your classes. If you click on your class, and so for some people that was a little buggy. I did notice that. You'll see a list at the top. That list is homepage, which we're not using, class notebook, which we are now using, classwork, which we're definitely using, assignment, grades, reflect, and insights. Reflect and insights I might have you guys use a little bit optionally, but obviously the important part for this class is classwork, assignment, grades. And then in channels, you'll see general, you should see general assignment announcements, DNS, well, you may not see DNS assignments, interesting videos, and questions and answers. If you do not see all of those channels, you can click on the triple dot, hit Manage Channels, and make sure all of those are selected, because then you'll see them. So question and answers is where you put your questions. Interesting videos tends to be where I put videos that are related to material that we're studying that you might find interesting, and I might at some point make those bonus. But under general, if you click on that, you see the chat that goes on in general, where I post announcements and so on and so forth. At the top of that, you'll see posts, files, more. So under files, that's where you would see all of the homework files and stuff like that. And if you hit more, you'll see a red thing that says calendar. And if you hit calendar, that's the calendar for the course, where you can click, and all of the YouTube meetings are posted in that calendar, and you can click and hit join meeting, and it'll take you to YouTube. So you can get to the calendar on your phone. That was what I was checking. Okie dokie. So let us go back to so I would call the third law an axiom. I'm just letting you guys know that straight up. Now, well, the zeroth law is more definitional. You're not it. There are occasionally, the books will throw a multiple choice question that the zeroth law, they'll say entropy of a perfect atomic crystal at absolute zero is what law of thermodynamics. So sometimes it appears as a multiple choice question. The truth is generally we're not going to ask such a trivial multiple choice question on a final, but that doesn't mean that the dental exam, pharmacy exam, MCAT exam might not ask that question. So it's a useful thing to know for Jeopardy type things. And it certainly does define a scale. Just like when we define temperature scale, we have to have some touchstones to define relative to. So it certainly does that. But on the order of importance in this course, that law, it's there. But it's not something that we're going to spend a huge amount of time on. Because what else is there to say? So it's kind of one of those laws that, okay. So now, all of these things were defined relative to the universe. But since we can't play with the universe in the lab, that means that we do sort of need to kind of divide the universe up. So we take the universe and we divide it up into system and surroundings. Now, most of the mistakes made in thermodynamics happen because of this. So there is a book, you guys can find it, you're welcome to try to read it. There's a book called Scientific Creationism. And it is trying to recast the laws of thermodynamics from a creationist standpoint. It's kind of the starting of, if you wanted to teach science from a creationist standpoint, here's where you would start. And the mistakes that are made in that book start from the very beginning, and it starts from right here. It starts from, well, what it really starts from is, I don't think I asked this question of you guys, but maybe I did. I may have asked it in 113. It starts with a lack of understanding of nothing. So, we have the Big Bang, we have a universe, the universe is, quote, expanding. What's beyond the universe? Because if the universe is expanding, what's it expanding against? See, there's always questions. So, what's it expanding against? What's there on the other side of the universe? Yeah, see, the answer is nothing. But our brain, our human brain goes, but what's nothing? You see? And that's the contradiction. That's the fundamental schism. I mean, when you really think about that, or at least even when I think about that, it makes me tense. It makes me worried. God, what is beyond the universe? What is it expanding? And nothing. That's the point. The universe is everything. It's expanding against nothing. There's nothing. But, and my brain goes, but, you see? Because we live in a world, we interact with stuff. And to us, air looks like nothing. But there's something in air. That's why we can feel wind. That's why we can hear each other talk. If we were truly in nothing, there would be no sound. So, our concept of nothing is developed based on our bodies, what we see with our eyes. And that's not nothing. From a, fundamental scientific perspective, that's not nothing. So, the vision of the universe into systems and surroundings, the problem is that barrier is an arbitrarily placed barrier. And because we're putting it there, we individually are defining the system every time. We have to be very aware of where we're putting that boundary. Because all of the equations that I'm about to write and derive and we're going to talk about and you guys are going to sit down and think about and try to memorize, they're determined, their form, their function, their shape, what they look like are determined based on where we put that barrier and what type of barrier we put there. So this idea of system surrounding and universe, it's really important and it's not easy and it's gonna cause you, well, it may not cause you sleepless nights, but if you're really a deep thinker, it's gonna bother you. So that's something to be aware of. Now, this barrier that I've just made a big deal about is an arbitrarily placed barrier that we set so that we can talk about the system versus the surroundings. But the moment we do that, since the energy of the universe is a constant, and I've just basically divided that energy into the energy of the system, I am not going to write any subscript for the energy of the system. I am going to write a subscript for the energy of the surroundings. That way you can very clearly see what's the system and what's the surroundings. Because the system energy, no subscript. surroundings, and universe. Sometimes you might see me write E sub U equals E plus E sub S, just because I get tired of typing UNIV. So it'll be written one of these two ways, but I will never put a subscript on the system energy, just because that makes it very clear. And I'm going to do the same thing when I talk about entropy and so on and so forth. That way it's always the same notation. Okay, now if I talk about the change in energy, so if you see delta, this is the capital Greek letter delta, so technically it's a capital. The lowercase version of delta is this. These mathematically are usually symbols for change. The capital delta tends to be used for large change. The lowercase delta tends to be used for small change, and for infinitesimally small change, we use D. And if you guys take calculus, this is going to be a derivative. So basically, big change, capital delta, smaller change, lowercase delta. And that's why that lowercase delta you'll sometimes see used for uncertainty. So if you're talking about the uncertainty in the measurement, you'll use lowercase delta because that should be a small change. And then if it's infinitesimally small, you use D. Now, if I'm talking about delta X, well, that would be the change in X. So I would have to have X at a final point minus X at some initial. If this were math. And the difference between the X where I'm at now versus the X where I was, that's the change in that variable X. Now in chemistry, we don't usually use final and initial point. We usually use state. So final state and initial state. And that's certainly what we're going to use in thermodynamics. And more importantly, these final and initial states are going to be defined by measurable quantities, like volume, temperature, pressure, and the amount of stuff. But we're going to get to that in just a minute. In physics, you'll usually call this 2 and 1. So you would write delta X as X2 minus X1, sub 1. So this tends to be physics. This tends to be chemistry, thermodynamics. But all of this is our way of representing change. And the difference between delta X and the lowercase delta is how big is that difference. And D, how big is that difference? Okay, so if I come up here and do delta E, of the universe, well, that would be E of the universe in a final minus E of the universe in that initial state. But wait a minute, first law says that the energy of the universe is a constant. So that means the energy in the final state of the universe is the same as the energy of the initial state of the universe. So that means that's 0. But this is also equal to delta energy of the system plus energy of the surroundings. So that means I'm going to write it up here. So that means I have energy of the system in its final state plus energy of the surroundings in its final state minus energy of the system in its initial state plus energy of the surroundings in the initial state. Or, now I'm going to regroup terms. Energy final minus energy initial, that's of the system, plus energy of the surroundings final minus energy of the surroundings initial. So that's delta E, the change in energy of the system, plus the change of energy of the surroundings. But all of that's still got to equal 0. So all of this is to say, if the energy of my system is changing, then that energy is flowing and matches the change in the energy of the surroundings. And the negative sign gives us the direction. So if energy in the system can either, if the system, if in order to make this change, I need to like heat the system, then I've got to flow energy from the surroundings into the system. If I want to cool the system, I've got to take energy out of the system and flow it into the surroundings. But the energy I take out of the system has to match the energy that goes into the surroundings in order for the energy of the universe to remain constant. So that's the first important definition. Now, that barrier. This stage, I'm going to go back up to here. This barrier, I've got to define it. I've got to use words to define it. So, we're going to take, again, a 5-minute break to allow you to think about this and ask questions. And after that 5-minute break, I'm going to define this barrier. So are there any questions, guys? Okay, so the this barrier. Now I've moved, for those of you that actually go back and look at these whiteboards, I've copied the diagram and moved it down where I have room to write and I'm not overlapping my writing. So this barrier that I'm arbitrarily putting up, and I'm going to give an example here in just a minute to show you how arbitrary that it can be. We use words to define it because we're humans and that we communicate with words, with language. So when we want to talk about this barrier, we have to use words. So when we get and derive equilibrium, there's basically three things that can occur across this barrier. I can either move the barrier, that's one thing that could happen. Two, I could move matter across the barrier. Or three, I can move energy across the barrier. Now, ironically, it's actually easier to do number 3 than it is to do number 2. So, but let's talk about the words we use to describe these types of barriers. So, if I move the barrier, so moving the barrier, that's either fixed or movable. No fancy words there. If it's fixed, the barrier's not moving. If it's movable, the barrier moves. So I'm not going to write any more there. I think that's kind of one of those self-obvious 2 words. Now I'm going to do the third one next. Energy. Adiabatic diathermal. And I've put them underneath fixed and movable so that you know it. Adiabatic means no heat flow across barrier. Diathermal means heat can flow across barrier. Okay, so an example. This cup, this is the cup I had my morning coffee in, which is now cold. This is a metal cup. This is a diathermal barrier. And that's why my coffee is cold, because my house is colder than the coffee was. So the heat from my coffee flowed out of this barrier, out of the cup, into the atmosphere. It also, until such time as my coffee matches the temperature of my house. It also flowed from the top of the cup out into the atmosphere, heat-wise. So this cup, the barrier of the cup itself represents a diathermal fixed barrier. This cup, if I'd wanted to keep my coffee hot for this entire lecture, this would have been the better cup to choose. They're actually made by the same company. This cup is a double-walled cup, so it's a vacuum cup. And that means there's 2 layers with some insulation between the 2 layers. And because of that, heat does not flow from here and contact the outside air except through the top of the cup. And if I had the top on it, that would minimize that too. And that's why this cup can keep something hot for however long it's rated. I think this one's rated for like 10 hours. And that's because even though this is the same metal as this cup has insulation between the inside metal layer and the outside metal layer. And that insulation provides an adiabatic barrier that keeps the heat from flowing from the inside, my hot stuff, to the outside. Or if I use this cup for cold, it would keep the heat from flowing from the outside to the inside to warm stuff up. So that's the difference between energy barriers. Now, mass. Impermeable. Permeable. This, no mass flow across barrier. Both my cups are impermeable, except from the top. Permeable, mass flow. Now, there are instances safety-wise where this idea of mass flow is a real problem. So, for those of you that work or know people that work in, say, nail salons or hair salons, a lot of times they will wear latex gloves. Now, the problem with latex gloves is they're cheap. They work great for food. Most food particles and food in the liquid and water, and most foods are cooked in water, will not flow through a latex glove. And that means a latex glove is impermeable to water, and it's perfectly safe for food handling. Latex gloves are not impermeable to most organic chemicals. So if you're wearing food-grade latex gloves and you're handling like the chemicals to clean fingernail polish off of fingernails, your skin is being exposed to those chemicals. If you're wearing latex gloves and you're using your hands to help like bleach somebody's hair, If that bleach is not an aqueous bleach, but even if it is an aqueous bleach, the hypochlorite can still permeate those gloves. And the problem with that is most people that use those gloves, they think they're safe. They think they are being safe because they think those gloves are providing an impermeable barrier and hence are protecting their skin. And our skin provides as impermeable a barrier as it can. But it's still got to be, it's not perfectly impermeable, because if it was, we would die of heat stroke. Because our skin is the way we release heat, and we do that in the form of sweat. Because that's how our body handles getting rid of internal heat. So if you're going to be safer, you would wear something called nitrile gloves. And that's what you see doctors put on in hospitals. That's the blue gloves. Those blue and green gloves. Those are generally nitrile. There are fewer people that are allergic to nitrile. There's a lot more people allergic to latex than you would expect, but there's fewer people that are allergic to nitrile. And nitrile offers more impermeability across a wider range of chemicals. That doesn't mean they're perfectly impermeable. And one of the things you have to do if you're working with a broad range of chemicals is you actually have to look up glove compatibilities. So there's this massive list that you can go find, and you look up the name of your chemical. It's based on name, and then you check to see, okay, I'm working with this chemical, and I've got latex gloves. Oh no, can't use those. And you find the glove that will work to protect you. Because like all humans, if we think we're protected, we're sloppier than if we're not protected. So generally speaking, if you weren't wearing gloves, you'd probably be pretty careful about not getting the stuff on your hands. But if you're wearing gloves, you think, oh, I'm safe, and then, you're just not as careful. And if it turns out your gloves are not the right gloves, you got more exposed than you would have gotten if you just hadn't worn gloves, because you would have been more careful. Now, that being said, I can have an impermeable diathermal barrier. Coffee cup. What I cannot have, what does not exist, I should have put this in a different color. Exists. So I can have a fixed barrier that also is any of the others, okay? So a fixed barrier can be adiabatic or diathermal, and it can be impermeable or permeable. So, in terms of fixed barrier, there's really no other restrictions on it. For movable, same's true. And that's because although on a movable barrier, theoretically, in practice, a movable adiabatic barrier is impossible. Okay, so having a movable barrier theoretically that is adiabatic is possible, but in practice, the moment you allow your barrier to move, that barrier is going to interact with the walls of that barrier could interact with the walls of what it's moving against, and that's going to generate friction, which is going to generate heat, which is going to transfer heat from one side of the barrier to the other side of the barrier during the movement. So, in practice, a movable adiabatic barrier where heat does not transition between system and surroundings is not possible. But theoretically, we talk about it all the time. So from a theoretical standpoint, it's kind of like in physics when they talk about in a Newtonian system, in the absence of friction, that's a movable barrier that's adiabatic. But the truth is there's no real system that's Newtonian. There's no system where you can have movement without friction. And that's actually the first and the second law. There's no system where you don't have entropy. Because friction is a way of dissipating energy. So, in real life, a movable adiabatic barrier is impossible. But we still will use that for theory. Now, never can exist an adiabatic permeable barrier. There is no way to move mass from a system to the surrounding without also moving energy. So you cannot have an adiabatic barrier that is also permeable, because you are going to move energy, you are going to transfer energy between system and surroundings if you transfer mass. So there is just no real way to have an I misspelled adiabatic, to have an adiabatic permeable barrier. There we go. So that one just never can exist. So, if you ever see a question with that, you know the answer is does not exist. And if it's asking you for a number or something, you need to Teams chat me and go, Professor, you were sleep deprived and you made a mistake. Because it cannot exist. Neoprene, that's a good question. In terms of, is it on par with nitrile? Neoprene and nitrile, I'd have to look at the glove. I'll come back to that at the end. Oh, class is at the end. We're at a good stopping point too. Good. So I'm going to define 3 more terms and then we're going to stop class and then I'll answer your neoprene nitrile question. Okay? Now, once we have a barrier, we can now name the system. So, we have what is called isolated, an isolated system. This is no mass or energy flow between system and surroundings. soon as you see isolated, this automatically implies adiabatic and impermeable. In the Newtonian case, it does not imply fixed. In the real world, it also implies a fixed boundary. But from a theoretical perspective, it does not imply fixed, but it does imply adiabatic and impermeable. We can have a closed system. This is no mass flow between system and surroundings. Most of the world we're in, you're used to a closed system. This cup, if I had the top on it, would be a closed system. And it would be maybe close to an isolated system. It's a pretty good cup. With the top off, it's more closed than isolated. Open, so closed system means impermeable barrier. Open system, mass and energy flow allowed. Now, the one final thing I'll point out, and we're going to start with this next time as we continue to build equations, is that those barriers can be arbitrary. And a lot of times the mistakes people make about things tend to be because they are they're using equations for a system, and they're using equations and they've got the barrier in the wrong place. Movable can be permeable. It just can't really be adiabatic. You can have a movable barrier that lets mass go through it. That's not an issue. The issue is energy going through it. So a movable barrier really cannot ever be adiabatic, but for theoretical purposes, we will sometimes assume it is. But a permeable barrier can never be adiabatic. And that's true in theory and in practice. So when we start next lecture, what we're going to start with is this picture, because this is a really good picture to explain where you put your barrier matters, where you define system and surrounding matters. So this is what's called a reflux apparatus. And what equations control this apparatus is really going to be determined based on where I draw the barrier on this picture. So that's what we're going to start with next time when we begin to talk about what this really means, the subtlety in this. But that ends the lecture, because I know some of you have to get to other classes. Now, in order to answer the question about gloves, so that actually looks like a pretty good glove compatibility chart, actually. Edit, copy link address. So I'm putting in the chat a particular link address, and I'm going to put the total screen up for just a minute so that you can see. So this is a gloves, an OSHA, and that's Occupational Safety and Health. You can't hand in the homework in person on Monday. The homework is due. If you're going to hand it in, you have to drop it off in the mailbox on Friday by 5 p.m. Homework will not be graded if it's dropped off on Monday. So you either submit it electronically as a single file, PDF file, through Teams, or you hand it in the Dropbox by Friday, 5 p.m. My research student is going to pull all of the papers out of the Dropbox on Friday. He's going to scan them, and he's going to email me those. Oh, yeah, sorry. If you gave it to me last class, you're good. I got it. Sorry. I thought you were talking about next Monday, not this Monday. Ignore the late notifications. Don't do that to me. Anyway, this type of glove selection chart, you'll see they have a butyl, latex, neoprene, nitrile. So this answers your stuff. And you'll see they've got very good, good, fair, poor, not recommended. So what you'll see is you've got acetone, ammonium hydroxide, and you just go forward. So like if you're working with amyl acetate, you should not use latex or nitrile latex. So for amyl acetate, and even neoprene and butyl are only fair. So amyl acetate, pretty much you need to be uber careful with amyl acetate with any gloves you want to wear, because it kind of goes through everything. You can see acetone, neoprene's good, latex, natural latex is very good, butyl is very good, nitrile latex is very good. So, sorry, for acetone, nitrile latex is poor, but natural latex is very good, butyl is very good, neoprene is good. So you really do need to be very aware of what you're using and what type of gloves you've got on. And so these type of glove charts are, like in my lab, I have one that's in the door so my students can check if they're working with organics. So now, one final thing for those of you that are still hanging around. You do not need to wear gloves if you're washing glassware. And in fact, if you're truly washing glassware and you're wearing gloves, you're probably less safe than you are if you're not wearing gloves. Because the glassware gets slick when it has soap on it, you've got gloves on, and it slips off your hands. And the reason for that is the standard recommendations for exposure to chemicals is, first step, wash with copious amounts of water. So when you're washing glassware in a sink, you've got the water on pretty much high blast, you got your hands in water, and you're washing glassware. So you are inherently washing with copious amounts of water, and you're also already washing glassware that has been rinsed 3 times, because that's what you're supposed to do if you're correctly cleaning glassware in a lab. Is you're supposed to rinse it once, dump that in the waste bottle, rinse it again, dump that in the waste bottle, rinse it a third time, and now you can wash it. So you shouldn't need to wear gloves when washing glassware. Just wanted to put that out as a safety thing. Okay, we are at the end for this lecture. I will see you guys on Wednesday. Monday's a holiday. Thursday is also a holiday, but I will still hold office hours 8 to 11 p.m. Well, 8 to 10 p.m. If anybody's there, I'll stay after 10 p.m. But if nobody's there, I leave at 10 p.m. Don't hesitate to ask for review, help, podcast topics in the question and answers section of Teams.